Continuing in Chapter 4, let's look at electrolytes and precipitation reactions. Now we know precipitation is going to be the formation of a solid ionic compound. And we know to make a solid ionic compound, we're going to have to start with ions. And so we need to understand that ions are electrolytes and what that means. All right, we can have a number of things occur when a solute dissolves into a solvent. So if we take and dissolve a solute into a solvent, we are going to have to break apart the bonds that hold the solute together. We're going to have to break apart the bonds that hold the solvent together. And then we're going to take and let the solute interact with the solvent. So if we have NaCl, we're going to take NaCl, if we put it in water, it is going to break apart into Na plus Cl minus. And the other interesting thing when we do this is that the Na plus is not just sitting there ignoring the Cl minus. It's going to take into account the fact that water itself is polar. And when we say water is polar, it really does mean that we have a little negative and a little positive end on the water. And because this is a negative and a positive end, this negative end interacts with the sodium, and the positive end is going to interact with the chlorine. What does that look like? Well, that looks like this. In this case, this is potassium chloride, but it's the same thing. It's going to break apart into K plus and Cl minus, and the chlorides are going to be surrounded by the positive ends of the water. Potassiums are going to be surrounded by the negative ends of the water, and they're going to split into pieces. So if we have this ionic compound, we're going to make two new pieces that are charged. Now, what does this do? Well, first of all, let's define an electrolyte. An electrolyte is a substance that when dissolved in water means it conducts electricity. So in order to conduct electricity, first of all, electricity is the flow of charged particles. So electricity is the flow of charged particles. So in order for something to conduct electricity, it has to have charged particles. So an electrolyte is going to have to contain charged particles. Well, this inherently is going to be ionic. If you put something in that's ionic and it dissolves in water, it's going to break into its ions. And these ions are going to be able to move. And when we move, we're going to have electricity. Now, if instead of having ions, we instead put something, for example, like sugar. Sugar is a molecule. This is not ionic. Therefore, when we put it in water, we're going to have no ions. And because this has no ions in water, this is a non-electrolyte. So we have electrolytes and we have non-electrolytes. They're going to be weak electrolytes as well, but we're going to save that for Chem 112. All right, so electrolytic solutions contain ions dissolved in water. Ionic compounds are the only things that are going to be electrolytes because they're going to dissociate into their ions when they dissolve. Non-electrolyte solutions are going to contain whole molecules dissolved in water. And the examples on things like that would be things like sugar. Or, for example, ethanol. Because we put a molecule in water, they're not going to break into ions, therefore it's going to be a non-electrolyte. The only difference here is some acids or molecular acids that do ionize when they get into water. We'll talk about that a bit later. So, some terminology. If we take an ionic compound and we put it in water, we say it's going to dissociate. Dissociate simply means it is going to separate. So sodium sulfide in water separates into sodium and sulfate. This is an ionic compound, and therefore this is going to be an electrolytic solution. Now, sodium sulfate will do the same thing, but the sulfate itself, because it contains ionic bonds, is going to stay intact and not break apart into its separate pieces. So please note, our polyatomics, when they dissociate, are going to stay in their state of polyatomic ions. So our NaCl, for example, will break into Na plus Cl minus. But if we had sodium nitrate instead, we're going to remember that it's going to break into the cation, and the anion is a polyatomic, and it's going to stay intact as the polyatomic. When we have a strong acid, and by the way, strong acid means strong electrolyte. Strong electrolyte means it is 100% dissociated. or ionized. And we use a different terminology when we have an acid because it's not ionic. We say that it doesn't dissociate. We say it ionizes into H plus and sulfate. And we'll deal with acids and bases in a different section. All right, so to know what happens, we have to look at these electrolytes, and we're being told that these are strong electrolytes, and we're going to put them in water. Now, we have to remember that if it is a nice monatomic ion, it's just going to break into its pieces, which means calcium is going to break up into Ca2 plus. Note this is chloride. Chloride exists as Cl minus, and that's what it's going to break into. Now, we're being told that nitric acid is a strong acid. Strong means it, in this case, ionizes completely. It's going to pull the H plus off, and the nitrate is going to remain intact, and it's going to be NO3 minus. Now, ammonium carbonate is also a strong electrolyte. Ammonium is an ion in itself. It is one of our few polyatomic cations. And because there's two here, we need a two here. And it makes two ammoniums. The carbonate is also going to stay intact, just the same way the ammonium is. And we're going to make two ammoniums and one carbonate. Please do not break these into their atoms. The only thing that breaks into a single species would be our monatomics. All right, let's look at some vocab. If we say something is soluble, it means it's going to dissolve. Now, sugar is soluble in water and so is salt, but how they dissolve is different. When a sugar dissolves, it is a non-electrolyte. When salt dissolves, it is an electrolyte. So we have to keep track of that. So solubility just tells us how much stuff can dissolve. If something is very soluble, it's going to have a high solubility. How much dissolves, we actually go to the lab and figure out. Insoluble. Insoluble means that we are going to make something that does not dissolve. Now, when we say this does not dissolve, this means that it's going to be a solid in our solution. It's not going to be up into the solvent itself. So a precipitate is an insoluble product that separates, and notice that these are separated from the rest of the solution, frequently sink to the bottom. And these are particular types of insoluble precipitates, and they are ionic, and so they're going to be a nice insoluble or precipitate solid. Now, there are tons of different compounds, so instead of learning everything that is soluble or insoluble, we're going to have some general rules, and here's our general rule. Rule 1, all group 1 compounds are soluble. So key here is all. Anytime you have anything that contains sodium or potassium or lithium, and even here ammonium, they are going to be soluble in water. Now, because these are ionic compounds, and when we say that this is soluble, it means this is inherently going to be a strong electrolyte. So what else is soluble? Anytime you have a nitrate or an acetate, and we have a nice ionic compound with it, they are going to be soluble. They're going to break into a strong electrolyte. Now, iodides, bromides, and chlorides are usually soluble. So now we start getting into the exceptions. The exceptions here say that if we put chloride with any one of these, it is going to be insoluble. So for example, AgCl is insoluble, or AgBr is insoluble. But if we said that we had ourselves some NaCl, well, NaCl, all group 1 compounds are soluble, so this is soluble. Now, when we want to indicate that's soluble, we're going to do AQ. AQ meaning dissolved in water. If it is not dissolved in water, we instead are going to put a solid here in telling us it's an insoluble precipitate. Now, what if it's not on the group 1 or this list? Well, for example, if we have copper chloride, we ask ourselves, is this soluble or not? Well, it's not silver, mercury 1, or lead. Therefore, copper chloride in the solution is going to be soluble. Sulfates are generally soluble, and we have a larger list of exceptions. Now, you're going to have to memorize these exceptions, or actually you don't need to memorize these exceptions, as these are on your equation sheet. All right, so now note here, we have group 1 or rule 1 right here. Rule 1 says that all group 1 compounds are soluble as well as all ammonia compounds. So my advice is to completely ignore these three because they're kind of obvious from rule 1. So let's look at hydroxide. Hydroxide is insoluble except with calcium, strontium, and barium. Sulfides are insoluble except with calcium, strontium, and barium. Carbonates and phosphates are just pretty much insoluble. The exception is rule 1, or group 1, or with ammonium. What does that mean? That means if you have, for example, aluminum phosphate, we look at this and realize aluminum is not in group 1, it's not ammonium, therefore this is solid. On the other hand, if we have sodium phosphate, we know that all compounds of sodium are soluble, therefore it is going to be aqueous and it's going to be soluble. So soluble or insoluble, KOH, this contains group 1, therefore this is soluble. And let's make sure we know that when we put this in water, it's going to break up into K plus and OH minus. Silver bromide. This is one of the insoluble compounds of bromide. It is going to be insoluble. And when we have silver bromide in water, it is going to be AgBr as a solid. Calcium chloride. This happens to be one of the chlorides that is soluble. Therefore, it's going to break up into calcium plus 2 chlorides. Nitrates. All nitrates are soluble. If all nitrates are soluble, we know this is going to break apart into lead plus 2 nitrates. Lead sulfate. This is one of the insoluble sulfates. We have to memorize that list, or at least be able to recognize that list on our equation sheet. And so if we have lead sulfate and we put it in water, it is simply going to be a solid in the bottom of our water. So let's consider a reaction. We want to consider a precipitation reaction where we're going to make an insoluble solid that's going to separate from the solution. And that's important because it's going to be ions left in our solution. So let's start with this. If we have lead nitrate and we react it with sodium iodide, it is going to make lead iodide and sodium nitrate. Now note, this is also a double replacement. This just means we're going to take the anion from one and swap it with the anion from another. Now note, the formulas aren't going to be the same because the charges aren't the same. But we can figure this out. This formula, or this equation right here that we've written, is called the complete molecular, or just the molecular. And we're going to use our molecular equation when we're going to take and do our math with our precipitation reactions. Now, the next one we're going to write is going to be our total ionic. The total ionic equation tells us if anything is aqueous and it's ionic, or it's a strong electrolyte, we're going to break into its ions. If it's a solid, we're just going to leave it as a solid. It's clearly not going to be aqueous and a strong electrolyte. So what would this look like? Well, we're going to start over here with the lead. Because all nitrates are soluble, lead nitrate is going to break into lead 2 plus, aqueous. We have 2 nitrates. We're going to put that 2 in the front, and we're going to remember to leave our polyatomics intact. It's going to react with our sodium. All group 1 compounds are soluble. And our iodides. It's going to break into our lead, or make, excuse me, lead iodide. Now, how do we know, first of all, that's going to make lead iodide? Well, if we look at our charges, our sodium is not going to stick to our iodide because that's already soluble. Our nitrate is not going to stick to iodide because they're both negative. So the only thing that can happen is the lead is going to have to stick to the iodide. We're going to put it together to get the right formula, which is PbI2, and we're going to apply the solubility rules. We know that lead makes insoluble compounds with chloride, bromide, and iodide. So this is going to be an S, insoluble. Now sodium nitrate is going to stay dissociated as sodium and nitrate. How do we know? Because we know all group 1 compounds are soluble. Now, what are we going to do from here? Well, we're going to notice that sodium and nitrate aren't doing anything. Sodium and nitrate are dissolved, and they're going to be sitting here in this aqueous solution as ions. They're doing absolutely nothing. And we're going to say that sodium and nitrate are spectator ions. Spectator as in they're just sitting and watching. If we take a look at our spectator ions, we're going to actually remove those from our solutions. We're just going to put a little X through them and see what we have that's left over. Well, what we have that is left over from this is our net ionic. Net ionic is like your net paycheck. They promised you $15 an hour, but you're only taking home 10. Yep, spectators are gone, and your 10 is what you got left over. That's your net. So in this case, our net ionic is lead 2 plus 2 iodides, goes into lead iodide as a solid. The sodium and the nitrate aren't doing anything. So a quick set of rules for our net ionic equation. We're going to start out with the balanced molecular, meaning everything is written as if it were attached, and we just write that out, and that's the equation we're going to use for our math or our stoichiometry calculation. Now, we're going to apply the solubility rules and see if anything actually happened. If we're making something insoluble, we are going to take and write it as a solid. That's our precipitate. If it's not soluble, we're going to write it as aqueous, and all things that are not going to be in our precipitate are going to be soluble, and we're going to write them as free ions. We're going to remove our spectators from both sides, and then we're going to write what's left over, and what's left over is going to be the net ionic equation. So let's do this one. We're going to have the reaction of sodium phosphate with calcium nitrate. So what do we know? We know that sodium phosphate is Na3CO4, and calcium nitrate is CaNO3. We know we're going to leave our polyatomics attached as we go through this and just swap what's attached to what. And we're going to apply the solubility rules as we go. So sodium phosphate. Well, all group 1 compounds are soluble, so sodium phosphate is aqueous. It is going to react with calcium nitrate. All nitrates are soluble, therefore that is aqueous. It is going to make sodium nitrate. Well, sodium nitrate, we know that sodium is +1 and nitrate is -1, so it's going to make NaNO3, and then it's going to have what's left over is calcium and phosphate. Well, to write the formula correctly, we have to remember that calcium is 2+ and phosphate is 3-, and the formula for calcium phosphate is going to be Ca3PO4 2. Now, we're going to balance it and apply the solubility rules. We're going to start with calcium phosphate because it's the most complicated formula. We have 3 calciums here, so we need 3 here. We have 2 phosphates here, so we need 2 phosphates there. And when we look at our sodiums and our nitrates, we're going to realize that we have 6. Now, let's determine whether or not these guys are soluble. We know that all group 1 compounds are soluble, so that's an AQ. And if we look at our phosphates, we know that phosphates are insoluble, and that's going to be an S. It's going to be a solid or a precipitate in this reaction. Now, this reaction right here, as written, is our molecular equation. So, step 2. Step 2 is total ionic. Total ionic meaning that if it's aqueous, we're going to break it into its free ions. Our ions are going to be 6 Na pluses plus 2 phosphates. These are all aqueous. Sapling in particular likes it when you put the aqueous there. Reacting with 3 calciums and 6 nitrates. That is going to break into 6 sodiums plus 6 nitrates and the calcium phosphate. As a solid. Now, to go from our total ionic, and notice we've got our free ions broken into pieces, we're going to have to write our net ionic. Our net ionic tells us that we're going to have to cross out our spectators. Our spectators are what does not change from one side to the other, and that would be sodium and nitrate. The only thing involved in this equation is actually calcium and phosphate. So our net ionic is 2 phosphates reacting with 3 calciums to make our calcium phosphate.